Good morning, everyone. Today we are diving into a fascinating world of map coloring. This presentation is a part of AAT concept video. My name is Zavia Esra. My roll number is 24951A12C8 and I belong to Department of Information Technology branch. This course is known as Essentials of Problem Solving. At first, it sounds simple, just color a map, right? But actually, it's deep mathematical problem. Map coloring is about assigning colors to regions so that no two neighboring areas share the same color. The main goal: use as few as colors possible while keeping everything neat and conflict free. And trust, it's not just about maps. These ideas help you solve real world problems in scheduling, puzzles like Sudoku, and even clip designing for computers. Basic concepts of map coloring. Let's get started with some basic concepts. What are these basic concepts? A map here is like a drawing where regions are represented as vertices in graphs. Coloring means assigning certain colors to those vertices. But if two areas touch, they must have different colors. The chromatic number is the fewest colors needed to color the whole map correctly. If a map can be colored with exactly k colors, we call it k colorable map. This definition sounds fancy, but they are the building blocks for everything we'll discuss today. What is a map? A map is a representation where regions correspond to vertices in a plane. Coloring. Assigning colors to vertices so adjacent ones differ. Chromatic number. Minimum colors needed to color any map without conflicts. K colorable. A map that can be colored with exactly K colors. In this slide, we are going to study about the four color theorem. Now, there's a big result in math, the four color theorem. It says any flat map that can be colored with most four colors, no matter how complicated it looks. The history of this um, the idea was first proposed way back in 1852, but interestingly, it wasn't fully proven until 1976, and it is needed for computer help. This proof was groundbreaking because it was one of the first times computers were crucial in solving major math problems. Instead of simple logic, the proof made massive exhaustive checking through algorithms. The four color theorem, it has a key statement, history, significance, and proof insight. Key statement is any planar map that can be colored with no more than four colors is known as four color theorem. History, it was proposed initially in 1952 but proven later in 1976. Significance, a milestone in graph theory combining math and computing powers. Graph coloring algorithm overview. This slide is about algorithm overview about graph coloring. So, how do we actually color a map? There are a few main algorithms. One is greedy, Welch Powell, backtracking, and distort. What is greedy? Quick and simple, but not always the best. Simply, it assigns colors in vertex order, but not always optimal. Welsh Powell, smarter by focusing on the busiest areas first. So, in Welsh Powell, colors vertices by descending degree for better contrast management. Backtracking tries all possible symmetrically. Systematic search to find valid coloring by trying possibilities. Distort adapts on fly based on what's happening around each region. So colors the next vertex with high saturation adapting to local constraints. Each has its strengths depending on what problem are solving. Greedy coloring algorithm. Let's zoom into greedy coloring algorithm first. It works like this. First, we have all the regions or vertices in same order. Then, for each one, we assign the smallest available color that doesn't conflict with the neighbors. Super straightforward. But here's the catch. The result depends heavily on the order we pick. Even though it's fast, Running in O vertices and edges time, it might not give the best results. So even if it's fast, it's not going to give the best results because obviously some edges are going to clash with the neighbors and it is not going to be proven well. Now the Welsh-Powell algorithm. Welsh-Powell algorithm is a smarter move. Here's how it goes. First, sort the regions by how many neighbors they have. Then, uh, highest first. Then start coloring, beginning with the busiest regions. The way we tackle the tricky parts first, which helps to avoid conflicts later. Here, step 1 is sort vertices by descending order. Step 2 is assigning colors with the highest degree vertices. Third step is optimization prioritizes coloring of most contrast region first. Complexity. It has complexity too. Sorting odds. O V square complexity manageable for one. This sorting step adds a bit of extra time about O into V square, but it's totally manageable for medium-sized problems. And we have D-star algorithm in. Moving to D-star, the one's even more adaptive. Instead of just looking at the number of neighbors, it checks how colors saturated a region is, meaning how many different colors are already there or used around it. It then colors the most saturated vertex next. This makes D-Star really good at handling weird or uneven maps, where some areas are way busier than others. So in D-Star algorithm, the step 1 is choosing the vertex with highest saturation degree. Step 2 is saturation degree is count of distinct colors on neighbors. Advantages adapts well to uneven regions distribution in complex. Complexity runs in OV square, similar to Welsh Powell, but more. In the previous slide, we learned about greedy, Welsh Powell, and D-star algorithm for map coloring. Next, we are going to see real world applications in cartography. Now, why do we care about map coloring? In cartography, real world map making is essential to make regions and easy to distinguish. Political map, geological surveys, and even school atlases use this principle. And there are real challenges like making sure that maps are accessible for colorblind people or respectful of cultural meaning of colors. This tool called Color Brewer that helps choose effective accessible palettes. Now, what is the purpose? Examples, considerations, and tools. Purpose is to ensure that neighboring regions are easily distinguished. Examples, we have examples of political maps, geological surveys, and educational materials. What are we considering while making this cartography? Accessible, including to the color vision deficiency, and it respects all cultural factors. What are the tools? Color assist in selecting safe and effective palettes. Other key applications of map coloring. But the applications go just map beyond the maps, which is scheduling, assigning time slots without overlap, how we do in Google Calendars. Sudoku. Um, Ensuring rows, columns, and boxes have unique numbers. We often use this in VSLI designs, arranging circuits on computer chips to avoid signal interference. Register allocations. In computer programs, efficiency, assigning memory space. Map color ideas show up in so many surprising places. Concluding insights on map coloring. To wrap up, map coloring might look like a playful art project, but it's deep and useful in areas of mathematics and computers. Thanks to four-color theorem, we know we'll never need more than four colors on a flat map. Today, we have discussed different algorithms from greedy ones to adaptive ones like distort, help us to solve coloring problems efficiently. And All the best. Thank you so much. Map coloring continues to inspire research, especially in graph theory and optimization. It has various advantages in computer chips and VSLI designs. Thank you so much.